I know in chapter 3.5 I want to show you something, some possibilities for graphical displays of FFP, so that you get a little bit more familiar with the system transfer function. We talk about system transfer function. That is a complete uncommon area, because normally we have nothing to do with frequency domain. So a good way to have a better feeling is a function, the mathematical expression. Better is, can we display the content in a good way? Problem of displaying is the following. Is a time signal is easy to display. A time signal is, say y is y of t is a function of one parameter. The output, the information parameter, the function is a real value and the parameter is a real value. So with a two-dimensional display, I can easily have one axis, a real axis, and the signal y is vertical of this axis, and the signal can be displayed as a line in a time diagram, or you can measure this with a scope. So we are familiar to work and think in time. The frequency function has a problem because p is complex, so normally the transfer function also is complex. Look, for this simple function, first order system has here a p. If this is complex, then the denominator is complex, has a real part and an imaginary part. So this function also is complex. So f of p has a real part of f and j imaginary part of f. That is the first thing. And the second thing is parameter. In opposite to the time is one real number. The parameter p is also a complex value. So if we has a real part sigma and an imaginary part omega. So if we want to display this function, then we need two axes vertical on each other for the input parameter sigma and omega, and the result are two real values which are independent, can be drawn on two further axes which must be vertical to sigma and omega. So we need a four-dimensional room, and that is what we cannot, what we don't have. Sorry. We need 4 dimensions. And so in our case, now we have a 3D movies, but no 4D movies. So it is impossible to display completely. There is no complete display of a system transfer function. So what we can do is we can ignore information. We can reduce information by deleting one or more than one part. Solution: reduction of information. The first reduction method is the following, and we get the so-called polar plot. We reduce the real part of the complex frequency. We just set this to 0. That means P is j omega. That means we get a new function. F of P then will be f of omega and is a reduced information, and the name, there's a new name, that is the frequency response of a system. Frequency response of a system. Note that we set the real part to 0, so the imaginary part is not 0. That means the function here, look for this example, if there is an imaginary part, this is real, we have still a complex function. Yeah, it's a complex frequency response, and this complex frequency response has a real part and an imaginary part. Real part and imaginary part. Stop. Imaginary part F. Or we can also say a complex number has a magnitude and a phase. Okay. The polar plot now draws the value, the complex number f in the complex plane, and the complex f plane, we can say. Complex f plane means this is the real part of f. Vertically we have the imaginary part of f. So we have a two-dimensional display, but we have here a value, here a value, and the parameter is omega. So what we can do is we can draw for each omega one point of f, and then we get say a curve like this, where we can say, okay, now this point has omega 1, this point has omega 2 value, this point appears if omega 3, and if omega is increasing, then we make an arrow points in direction of increasing omega. Yes, so for one frequency we get one point of f, and this point has a real part and an imaginary part. Let's do an example. We just want to discuss first the first order example 1 divided by 1 plus pt, our first order low pass filter function, and in the next step is I show you a more complicated example which is also documented in the workbook. Let's start with our first order low pass filter function. We set sigma to 0, so we get then f from omega is 1 divided by 1 plus j omega t. Okay, we get the following curve. This is the imaginary axis of f, this is the real axis of f, and we indicate the plane with this f plane. Okay, if omega is 0, we get a 1. So in red, say this is 1. The dimension from 0 to 1, that is the real number 1. If omega is 1, so I indicate omega, say with a blue color. So we say, okay, this is omega is 0. Let's calculate a second omega case. Now, f omega 0 is 1. what happens if omega is very large, goes to infinity. If this is very large, we have 1 divided by an imaginary point, an infinitely large point, so we get a 0 here. So we can say, okay, we have a red point here, and we can indicate this with omega infinity. Yeah, with 2 points I cannot define which type of curve this is. We know from mathematical scientists that a function which has only linear part in the numerator and linear part in the denominator, because this bilinear function has a polar plot, which is either a line, a straight line curve, or which is a circle. With 2 points we cannot find out if this is a straight line or a circle, so we need a third point, and this comes now. The third point, let's do with the following value. If omega is 1 over t, later we will call this corner frequency, what happens with my function? If omega is 1 over t, this is 1, and we have a value 1 divided by 1 plus j. And if we convert this, if we expand this with the conjugate complex denominator, then we get 1 divided by square root 2, 1 minus j. So, complex calculation. This is a value, a red point, which not with square root 2, sorry. Natürlich Quatsch. 1 divided by 2, 1 minus j. So we get now a point which has a real part here and an imaginary part, half of j, which is here. So this point is here, and then you can see, okay, a straight line is not possible, this must be a circle. This is a circle starting with real part 1, going through this point, 0.5, 0.5, ending in the origin of my diagram. So, okay, this is the polar plot of this system function. The question is, what can we do with a polar plot? I just show you one relation. We draw Cartesian coordinates here in this diagram. What happens with these polar coordinates? I can show you the relation of the polar coordinates with following drawing. Assume we have here a point, then the connection to the origin, if you draw an arrow from the origin to this point, then the length of this point is the magnitude. Oh, kann man aber schlecht sehen. Length of this point is the magnitude. Viel besser. Is the magnitude f, and this angle is the phase phi. Okay, that is the magnitude. With this we can understand that is the gain of the system function. The gain means the ratio output over input, and if we have a sinusoidal signal, then this is a phase shift between input and output sinusoidal signal. This is a polar plot. I show you a more complex example. Black, more complex example. Second example. Demo F, I call this Demo F. C workbook. Page 12 to 15. 4 pages for this graphical function. This is I show you the copy of the transfer function. So this is a copy of the transfer function coming from these pages of the workbook, and you see in the numerator is just a simple p, and in the denominator a 4th order polynomial function with p to the power 4 plus some other coefficients. All coefficients are available down to 14.4041. This is the demo f function I use to demonstrate more complex filter functions than a simple first order system. The polar plot of this curve can be seen in the workbook. Let's have the quick look on the workbook polar plot response drawn with my Rec C# simulation program. You see here the diagram. This is the origin. You see here the 0 and here the 0 on the axis. So this is the origin, and the polar plot starts here with positive phase going through the real curve, and then makes just this curve around all 4 quadrants, ending up here with very high omegas again in the origin. Yeah, you see my program has here used not enough points to have a smart curve, but I think this is accurate enough to understand what this is for a filter. You see omega 0 and omega infinity has no gain. That means for low and for high frequency, no gain. This is a bandpass filter. Only in the region of some omegas, here we have the relevant amplitude. So this is the polar plot of a bandpass filter. But I stopped discussion about polar plots because polar plot is in my lecture not very important. So let's have a look on the next type of display. That is chapter 3.5.2, the pole zero plot. Pole zero plot, which is a very simplified diagram, just a 2-dimensional diagram which displays poles and zeros. Before we discuss this, what is a pole and what is a zero? A pole P infinity is that where the transfer function goes to infinity, and a zero, with like the name can tell us, yeah, P0, this value, if we replace all p's with P0, then the function is 0. So the pole makes the denominator to 0, and the 0 makes the numerator to 0. In example A, this is simple. Here we have no 0 and one pole for which P goes the denominator to 0. Very simple, we can calculate this. 1 plus P infinity T we set to 0 is the calculation equation for the poles of our first order filter function. So P infinity is negative 1 over T. In the case B, we can at once see what for a 0 we have. Yeah, the 0 of case B, example B, and this is example A. The example B has a 0 at 0, and the poles are the zeros of the denominator polynomial function. Here you have, of course, to use the calculator in your PC or within a relevant PC program, or your handheld calculator who can solve equations, polynomial functions, and root finder or anything else. So the result will be the following: p infinity, there must be 4 poles, because a polynomial function of degree of 4 has 4 zeros. And I give you the results. P infinity 1 and 2 are negative 0.2, real part, plus and minus J 1.5, and the other both poles, a complex pole pair 3, 4, has the same real part, but the imaginary part is in 2.5. Yeah, if you solve this equation set to 0, these are the 4 zeros, so we call this poles of the function because this is a polynomial function in the denominator. In the drawing, a pole is marked with an asterisk, this is cross sign, and a 0 marked with a small circle. And the display is done into the p-plane. P-plane means here we note complex p-value, so the horizontal axis is the real part of p, the sigma, and the vertical axis is the omega. And if we do this in different colors, so case A displayed in the way that we can say, okay, there is a negative real pole at the distance minus t, and if we mark this with red, then the B part has a 0 here, and on the negative side we have 4 poles, so you can say this is 1.5 and this is 2.5. Here we have an asterisk, here we have an asterisk, and the same as with negative, negative, minus 1.5, minus 2.5, and we have here an asterisk, here an asterisk. So the pole 0 plot of our demo f function is in red, is existing on 4 asterisks and 1 circle, and the pole 0 plot of my first order low pass filter is just 1 asterisk on the negative real axis in my p-plane. You can ask, okay, what can a scientist see with this pole 0 plot? I can answer with some experience. You can see with just one glance on this what this is for a type of filter, but normally this is for beginners not very helpful, but it is the transition to the next graphical display, which is very helpful in understanding. I think if you have understood what is a pole 0 plot, then you will follow me with my next example. This is the magnitude mesh plot. Yeah, the third part is magnitude mesh plot. Let's look what this is. 3.5.3 magnitude mesh plot. What happens here in this case? It is a 3D display, 3-dimensional display, which of course then has to be copied in a 2-dimensional display of my paper. Yeah, 3-dimensional display. What is with the 4th dimension? Very simple. I display the magnitude value over p-plane, ignoring the face. Yeah, I throw away all information dealing with face. I display f magnitude over the p-plane. That means for each point here, vertical to this, so vertical out of my display, I make a point for the magnitude value. Yeah, for each point in the p-plane, I make vertical to this a point of the magnitude mesh plot. Then we have to say, okay, first we should know that this curve is has a symmetry between the horizontal sigma axis. The information in the negative imaginary part is a copy of the positive imaginary part that has something to do with real coefficients of my polynomial function. You see with the poles this is true. So this information here in this area is not new. So the complete lower area of the p-plane we can ignore because this gives not new information. Next point is cost of stability. There are no poles here in the first quadrant. Otherwise the filter is unstable and then we cannot use it. So what we do is we just display the mesh plot over the second quadrant. This is the second quadrant, this is the first quadrant, this is the third one, and the fourth one. We can say the display over the p-plane in the second, only in the second quadrant. And then, okay, you have a three-dimensional display. I show you what happens here in the case of my demo F. Here is a pole that looks like a tent. Yeah, the display has very big similarities with a tent. The poles are the poles. Poles are, and the name of the stick of a tent is really a pole. Poles are poles of tent. Zeros are pegs. Yeah? A peg, in German, Deutsch, Hering, put the tent to the floor, to the ground. Yeah? For large omegas and sigmas, high frequency for large omega sigmas, and now I have to go to the names here. The numerator order is m, the denominator order is n, and now I can say if m is smaller than n, which is in many applications and in control systems the case. For large omegas, if m is smaller than n, is f magnitude very small, goes to 0. So the tent in the distance to the poles touches the earth. Touch the earth, the ground, yeah. And the last point is the cut curve over omega axis. That is the interesting case. The cut curve of the omega axis is the amplitude curve. The amplitude curve of the filter is the amplitude, the gain curve of the filter. Gain of filter. Let's look to the magnitude mesh plot of this curve that is displayed in my workbook. So just open my workbook at the right page and then we can discuss this curve more deeply. Yeah, with one of my tool programs I have created this display. Note the axis. This is the origin. Here, this is a negative sigma axis. This is the point -1. Then here, this is the omega axis. This is the point 4, and this is vertical to this axis, and that axis vertical to this. This is the magnitude axis, and this is the value 2. Note that we have here a pole roundabout here at this point. I cannot draw here. Okay. So this is the first pole, and this is the second pole, which pulls the tent up. This is a 0, a peg of the tent, and you see if you are far away from the origin, the tent goes to touches the ground. What is interesting of this mesh plot is, now look vertical over the omega axis, then you can see here the gain of the filter. Here's the gain small, it's 0 at 0. For DC we have no gain. Then there is a gain increase here with 2 peaks, and then for higher frequencies the gain goes down to 0. So here you can really see the bandpass filter function of this filter. And in the background you can see how this filter is designed. Here are 2 poles, here a peg. If you want to have steeper behaviors here from the passband to the stop band, passband. If you want to have steeper gradients, then add here some pegs on the omega axis and we get Cower filters. Yeah, the filter designer works with this type of three-dimensional display of the magnitude curve to design nice filter functions. Yeah, I think this is a little bit a help to understand what information is hidden in a transfer function. I just stop this video and show you the fourth version of display of the graphical function, which is this is the amplitude and the phase curve, the filter, and this then is the next step into the Bode plot in chapter 3.6, but that should be the next video.